So, last time we learned about the capacitance of a metal charged sphere.
सर
Yes.
सर मेरी प्रैक्टिकल क्लासेस होती हैं 9 to 3 सैटरडे को, तो मुझे टेस्ट देना बहुत मुश्किल हो जाएगा। प्लस मेरा AS A2 दोनों के टेस्ट सेम टाइम पर।
Salma, you have 12 hours to do it. The summation will close at midnight. Do you understand?
ओके ओके ठीक।
When you come back, because there is a time difference. Some people are in Saudi, some people are in Bahrain, some people are in other countries. So I have kept the whole time. You can take it after the class. Just do it.
That's an online test, that's why I was saying this. Got
Yeah.
it.
Yes. All right. So today we are starting with magnetism. All right, Abu Bakar's favorite topic. So let's begin. Okay. So about 1 second, please. All right. Now, now, kids. So about magnets, just remember that it's basically objects that produce a magnetic field. It is an object with dipoles. Dipoles basically means obviously it will have a north and south, as you guys know. Is my voice okay? You kids? Okay. So now about magnetic field, basically a region where a magnetic pole experience experiences a force. This is what you are right. Then you have magnetic field strength. It is measured in Tesla. And the symbol for that is capital B. Now remember that, please write this note. Earth has basically metals inside its core, and because it is spinning, current flows. So because of this current flowing, a very weak magnetic field is created. All right, kids. Very nice. Please write this down. Okay. Now, now you're going to learn how to create magnetic fields or draw them. It's pretty simple. Outside the magnet, the field always go out from north and in from south. Like that, like that, like this, and like this. So out from north, in from south. If there are like opposite poles, the magnetic field goes from north to south like this. And then you can draw it like that as well. In from south. Same goes for this one. Out from north. Whenever you have opposite poles, so you guys need to understand that opposites attract, which means their forces are going to be towards each other. When it comes to like poles, what happens is that the magnetic field does not connect between the two. It creates a shape like this, which is the same in from south, out from north. In this region, you will find a spot which is the null point where the field doesn't exist. And obviously, you guys need to remember that same poles repel. So their forces will be like this. Now this is an additional one. If something like this comes, which is highly unlikely, but still you should remember fields do not connect with same poles nearby. And sorry, this is not okay. Should be a bit on this side, bit on that side. It gets repaired like this actually. So it has two null points. One region is right here, and the other null point is right here between the norths and between the souths. So you guys need to remember that. The more important thing is this side note, which is basically tells us what happens inside. So actually, when you draw a field from north to south, what you're really doing is it goes in loops. So it connects like this. So inside the magnet, the field is going from south to north actually, like that. Because it needs to complete the whole loop. So you guys need to remember within the magnet, we have straight lines from south to north equally spaced. Also remember this very important point that field lines go in discrete paths. So they have their own paths and do not intersect. Like you would never find a field going like this. It would not intersect with each other. They will always go on their own path in complete loops. Is it clear, everyone? Hajra, Zainab, Abubakar, Samir, Salma, very good. Very, very nice. Write it down, please. Interesting. Very nice. All right, kids. So I'm going to go to the next then. And we are now going to talk about the Maxwell's field strength experiment. And it explains us how the field is created. So remember, there are two inseparable fields which are mainly electric, which we learned in the previous chapter, and magnetic interact. What happens then? If there is an electric field, there's a condition attached to it. So there can be also a magnetic field. Now, the magnetic field can be there. So it is always there, in fact, when a charge has an electric field. So when it moves, please remember, charge needs to move. When it moves, current flows and magnetic field is created. If there is no movement of charge, you still have electric field, but you do not have magnetic field. So it is very important for charge to move in order to create the magnetic field. Please remember this. Now, obviously, when you look at the field that generates because of the current flowing, the field is strongest at the center wire, but as you go out of it, so the magnetic field strength reduces as you increase the distance r, which is basically the distance from the center of that particular wire. So please write that down as well. Magnetic field has a decay nature. The circles are concentric. Concentric means that they basically originate from a single center and are not equally spaced. So as you can see, initially the circles are small. As you go further and further, the gaps between them increases as well. Please write this down. Now you need to understand that Maxwell has given us the right hand grip rule to find the direction of field. So if you have basically a circular current and a linear magnetic field, which means the current, this side is connected to positive, this side is connected to negative. So the current is going to go like this, curl back like this, and then go back here. So if this something like this is happening, just remember that your thumb should point towards the north, and your fingers should curl in the same direction as the current. So that's basically back of your hand, and this will then be creating north, and this will be creating south. So I just want to tell you that this one, in if it's a circular current and linear magnetic field, fingers curl in the direction of current, and the thumb basically shows you the north pole, like that. Again, within it, the field will be like equally spaced and straight line, but when it goes out, it just curves like that. It goes like this. This is the magnetic field. Please draw this. This is very important. Please use the right hand to do this. Do not use the left. All right. Hajra, Zainab, Abu Bakr, Samir, Salma, everything's clear? Very good, kids. Excellent. Abu Bakr and Samir, wake up, please.
Yes, sir.
So, now let's go to the next. Now, when you have basically circular magnetic field and a linear current, then what happens? So, what you got to do is you got to put your thumb in the direction of current, and then your fingers will curl like this. You can try as well. So these should be your fingernails, and this is your hand. So this is the right hand, please. And then obviously, because your fingers are going to curl in anti-clockwise direction with respect to this type of current, so then you will have a field like that. All right, kids, keeps on going like that. So the thumb shows you the current direction, and the fingers curl basically shows you the direction of field. So field is always circular in this. Very nice. Now let's go to the next. Now we need to basically learn how to find the magnetic field strength on a single wire. So suppose the current is going this way. So you guys need to put your thumb down and turn your fingers, curl them, and you would analyze that your magnetic field would be going like that. It's in a clockwise direction. So if I say that from the center to this is the distance r from the center of the current. So remember this particular point that the formula for this one is going to be B equals mu naught I divided by 4 pi r. Now let me explain this. The good thing about these formulas are that you don't need to remember them. Just need to understand and remember one quantity in this. This quantity that you see here obviously is the magnetic field strength. This quantity has a value, it's a permittivity, it's a constant, and 4 pi times 10 raised to minus 7. And I want to tell you that please remember this. This is something you guys need to remember. There is nothing else you need to remember. Everything will be given. I in this is the current that flows through this wire, and R is the distance from center of wire. Everything else is the same. Now within this, I want to tell you something very, very important. If you look at the field from top, you'd realize that actually it makes a complete circle like that. And because field is moving, either it could be clockwise or anti-clockwise. So every point has a particular direction of magnetic field strength. Why? Because it is a vector quantity. So if I say it wouldn't be wrong to say that for B will be in different directions. B will be in different directions at each point. Since it is a vector, so you guys need to remember that the direction is always tangent to the field. All right, kids. So you got to draw a tangent to find what will be the direction at that point. What is the red circle? This is a field. Just like, Salman, if you look at this from the top, you will see full circles, like this.
Okay.
Okay. I hope everybody is clear. If you have any
Yeah.
questions, yes, Salma.
The direction is always tangent to the field. Direction of what?
It's tangent to the always tangent to the field.
Yeah, like what direction are we talking about?
So if the circle is like this, right? It's moving like this.
Hmm.
So you have to draw a tangent. So at this point, the direction of magnetic field strength is this way upwards. At this point, it will be towards the right. Yeah. So if you draw like direction here, it will be like this. You understand? Tangent.
Yep.
Very good. All right. Similarly, if you have a solenoid, they give you a solenoid, there are a couple of things you guys need to remember. First of all, they will be interested in only finding the magnetic field strength at the center, nothing else. That is the only thing in our course. There will be few quantities that you guys should be aware of. Obviously, the formula is going to be given to you. The first quantity is N, and then you have another quantity which is L. So let me explain this. These N and L are related to small n equals to N over L, where the small n is the number of turns per unit length. N is the total number of turns that you have in the solenoid, and then this L is the total length of solenoid. So from the wire that is coming in, and the wire that is going out, that is basically the length that you measure, and you can count the number of turns. If you divide the number of turns with the whole length, you will find the value of small n, which is number of turns per unit length. Now, why is that so important? Because if you want to find the magnetic field at the center of this particular solenoid, it would be mu naught, which has the same value as 4 pi times 10 raised to minus 7 into n into I, where I just want to tell you this. P is the magnetic field strength. Mu naught is 4 pi into 10 raised to minus 7. Like I said, n you already know. And I is the current that is going through. Very, very nice. Okay. Yes, Zainab, Hajra, Abubakar, Samir, Salma, everything is clear. Let me know, please.
Yes, sir.
All right. Again, you guys don't need to remember anything. Just know what these things mean when they give you the formula. All right, then. So let's move to the next. If you have flat circular coil and then the coil goes like in and out, just remember this. They will ask you to find the magnetic field at the center again. And this time, this magnetic field will be equal to mu naught I over 2r, where this r is basically the distance from one wire to the center. So remember this again. This is basically magnetic field at center. This is 4 pi times 10 raised to minus 7. This is the current, and that is the distance from wire to center. All right, that's pretty good. That was the last one, actually. Okay. All right, kids. Now let's go to the next. Now, in linear conductors, I just want to tell you some of the sign convention that we need to use. If the current is going into a conductor, just remember to show in 2D, we use a circle and a cross, or just a cross, that's fine. For this one, if the current is coming out of the conductor, we use a dot. Basically, this sign means into the page, and this sign means out of the page. Whenever, if you want to rote learn this, it's pretty simple. You don't even have to use the grip rule. Whenever you have a um, wire that's carrying current inside, you will basically have a clockwise magnetic field around it. And whenever you have a current coming out, you can check right now as well. You will always have an anti-clockwise magnetic field around it. Now there is though a disclaimer that I want to put forward, and that disclaimer is that it only works for conventional current, which means the current that moves from positive to negative, not the other way around, please. But you can remember like this if you want to. Otherwise, just remember the symbol. You can point your thumb into the page or out of the page and then grip it to see where the feet is going. That's always the better way. Very, very nice. All right, kids. Now going to the next. So in this question, it says state two conditions in which does not experience a force. And I told you that for a charged particle create its own magnetic field, it must be moving. So if the charge is stationary, it would not create its own magnetic field, and a stationary charge would then not feel any magnetic force. The other thing is the charge might be moving parallel to the field. In order to feel the force, you guys need to move the charge perpendicular to it. Otherwise, there will be no force in it. Yes, Salma.
सर क्या ये नहीं हो सकता कि दो मैग्नेटिक पोल्स जो हैं वो सिमिलर हों तो रिपल्जन की वजह से वो फील नहीं कर पाएंगे कोई फोर्स?
Two magnetic, but they're not talking about poles here. They know the magnetic field exists there. They've said there's a magnetic. So if there are two similar poles, then I've told you that between those poles, you don't have any magnetic field here. Null point. But it's a magnetic field. Now we need to address that only. Is it clear?
Okay, I think your voice is lagging, sir.
Okay. Right. Or should I change the internet? Probably should. Wait a second. Huh? Okay. All right. Is it better now, Salma?
Yes, sir.
Now, this question came very recently in 2021, and I suspect that this question might come again because this is a new type of question that was not given before. And I just want to bring your attention to this because it has a helical spring. Helical spring means the normal spring that we see. And it says that when it's coiled up and the length of the spring is measured before the switch, so we know what is the length like this, right? So each spring has a length, obviously, so they have found it. And then they've said the switch is closed. When the switch is closed, it says a magnetic field is set up and each coil of the spring, around each coil of the spring. By reference to these magnetic fields, explain why there is a change in length in the spring and state whether the spring extends or contracts. Now, please understand this important part. When this switch is closed, obviously, you will see the current from the positive side to go like this. It will move here and then move back here and then here and then here and then move here back to the negative. Do you guys agree with that? Now, please understand this very, very important part. If you just look at this length, kids, this length and this length, just focus here. You might see that actually what's happening really is that it seems like from the front, these are two single wires that are right there. Get it? And the current is moving like this. I'm only looking at the yellow section here. Let me zoom in so you can see. I'm just looking at, let me put a different color. What color should I put? Okay, green. This section only of the wire. You guys agree? So if I'm just looking at this from the front, I will see that these look like a straight lines that are going like this. Now, what you guys then need to understand is that actually these two straight lines, when we have two straight lines, actually they could be like going into the page or out of the page. You're looking at it from here. So what happens then is if you make the grip rule, your thumb should be out of the page. You will see a field on the first one would look like this. So it is going to be anti-clockwise like that.
Sir,
You
can
guys
you
agree?
explain why is it out of the page?
I just basically whether you make them into the page or out of the page, it doesn't matter. What I'm saying is that you should understand they're both in the same direction. That's why I made both of them out of the page. You can make them into the page as well, it doesn't matter. Okay.
Yep.
Okay. Now, if you create the field of this one as well, it will also be an anti-clockwise field. The reason being that actually these two are, your thumb should be out using the grip rule. Now, please try to understand the center of this. We've just learned, we're going to look at the center. They're going to ask you about the center. This section of the field and this section of the field are basically opposite of each other. Do you guys agree? And what we have learned about opposite, do they attract or do they repel? Yes, kids. Opposites attract. Very good. So opposites attract. If these two wires are going to attract, then what happens is that they're gonna twitch in such a way that they're gonna get closer to each other. Do you guys understand that? So the average spacing between the coils is going to decrease. Understood? Hajra, this point is clear. Zainab? Very good. Excellent. Abu Bakr, any question? Very nice. So now we need to write everything between these lines. So we have 4 mark question and we need to write 4 points here. So please see how we're going to address these. First of all, if I were you, I would start writing it like this. I would say each coil will create its own, oh my god, that's not fair, its own magnetic field perpendicular to movement of current. Now that should be my first point to establish why there is going to be an attraction, because I need to tell them, I need to tell the examiner that I know that whenever there's a movement of current, there will be a field. The next thing I'm going to write, the two magnetic fields of the turns interact and exert a force on each other. So now I have established that there will be a force because I want to see, because it says what happens when the switch is closed, a magnetic field set up around each coil, and what happens then. So you've got to explain that. Number 3. So the force between the coils will be attractive as they are created in opposite directions between them. Now, the force will be perpendicular. Like I said, force exerts when you have a perpendicular movement of charge, right? So the force will be perpendicular to the movement of current that will cause them to contract. Is this clear, kids? Now, obviously, I have just put them into 4 points. You can write it between the whole lines, don't leave spaces, you will get the full answer here. But you have to make sure always in these type of questions, when you have a write-up, you need to remember that you guys always focus on 2 important things. Number 1, direction of current that leads to then direction of magnetic field. The magnetic field direction will lead to force. Now here's a important part, that force will be perpendicular then, and force is always perpendicular if the charge is perpendicular to the direction. Otherwise, if it's parallel to the magnetic field, then there will not be any force acting there. Is it clear, kids?
Sir, can you repeat the last point?
What I'm saying is the force will be perpendicular to the direction of magnetic field and the current. If the charge and the magnetic field are not perpendicular, then there will be no force. Understood? And that's why when you asked me this question earlier, that's why they started off with these 2 points to remind you that obviously they know if somebody knows this, they will be able to do the last question. Otherwise, they won't be able to do the last question. Is it clear? Very good. Please write this down. Very, very important stuff here. Now, like I said, this question came in 2021. And then, interestingly, and never before in my whole life, when I was doing A levels, I did like 10 years, I did papers from 1990. You guys did papers you will be doing from probably 18. So I gave my A levels in 2009. I've done 20 years before that. You will be doing 20 years before your exam. And I've never seen these questions come, which means that the examiner is now looking forward to it. So please do learn these. This is why I have also included another question just after this that you guys need to do. It's your duty to do these. This is the homework. This is exactly the similar sort of question, and it came in 2022. So remember, in 2023 they did not give this question, which is a possibility right now that they will again test students on this one. Is it clear, kids? All right. Now please do this, and then let's move forward. So the next thing we're going to do is basically the theory behind the Fleming's left hand rule. It's pretty simple. Just remember, if you're looking at the section of wire from this side, so this is your eye. So you would see that there is a north pole on this side, south on the right side, and the current is going into the page, as you can see in the next diagram. Well, then you guys need to understand that the field between the north and the south is going to be something like this. That's not fair. Okay, it's going to be something like this. But then the current that is passing through will have its own field. How? You put your thumb into the page and then you turn your fingers, you will find out that the field due to this current is basically a clockwise one. Now, I'm gonna zoom in to explain it better. The field is clockwise, so it will be like, oh my god, that's not fair. So it will be like this, and this, and this, and this. Right, kids? Now just focus on this top section. You might see that the field of the wire and the field of the magnet, the permanent magnet, are in the same direction, isn't it? What do you guys say? Right? So basically they complement each other. But then if you look at the bottom, you might see that the field of the wire and the field of the magnet are in opposite directions because the field of the magnet is going towards the right, whereas the field of the wire is going towards the left, which basically causes a sort of interaction. All right, so let's talk about that interaction now. So in this one, this interaction between two fields causes high flux. Flux is basically another word for interaction. So density means there's a larger density above the conductor in this case, all right, and less at the bottom. Now, what then happens is, because of this, the field at the top sort of combines and creates a more dense field at the top because it's basically going in the similar direction, like that. This is the net field I'm drawing. At the bottom, you do not have dense field, which causes a sort of a pressure difference, sort of concentration difference, I could say. So in this section, you will see high concentration of magnetic field. And in this section, you will see a low concentration of magnetic field. Because of this, the conductor inside is going to feel a force downwards because it's being pushed down by the field. Is that clear, everyone? Very, very good. Very, very good. All right, write this down. And then this is basically the reason why Fleming left-hand rule was there in the first place. Anyhow. Okay. Now I'm going to show you a diagram of Fleming's left-hand rule. Let me find it out. I don't know why I didn't paste it. Okay. Let's take this one from the company that bankrupted. So let's do that. Okay. Now this is the proper way of using left-hand rule. So you guys need to remember the thumb here shows you the force, which is the thrust. Your index finger will be magnetic field direction, and current will be the middle finger. Now, what I want you guys to understand is that all these three things, be it force, be it magnetic field, and the current, all of these are 90 degrees to each other. All right. All of these, let me write B, all of these are always 90-degree to each other. Now, I just want you guys to then focus on one pro tip that I want to give you. And this is that always align the magnetic field first, which means your index finger should point towards the magnetic field of the magnet first, and then you can either rotate it like this or the other way to align the current to find the force. Please write this down. Okay. Now let's check out this one. So the equation of Fleming's left-hand rule is pretty straightforward. It is nothing of um, high concern. The formula for this is F equals to B times I times L. I remember as force equals to Bill. If you remember, if you want to, you can use that one. जी बेटा क्या चीज पिज्जा मैंने नहीं खाना बेटे मैं नहीं खाता मैं क्लास के बाद देखता हूँ ठीक ओके सो आई एम गोना बेसिकली this is the magnetic force. This is the magnetic flux density. It is the same thing as magnetic field strength, doesn't matter. This is in Tesla. This is in newtons. This is your current. These are all SI units, okay? Amperes. And this is the length of the conductor. Length of wire exposed. Now, when I say exposed, it means the length that is within the field. Okay, this is within the field. So that would be in meters, obviously. Now, for this question, if they give you a force at an angle, just don't forget that I told you that the force has to be perpendicular. Everything has to be perpendicular. So you got to make components of it. Obviously, the current is going in this direction. So then it will be, you will make a component here. You will also make a component here. This will be I cosine theta. This will be I sine theta. You can also take length as the one, doesn't matter, length sine theta or that one. And then basically the force and angle would be F equals to B times I times L, and you have to multiply the perpendicular component with it. So remember, if you put sine 90 in your calculator, it will give you 1. And if it is parallel, you put sine 0, it will give you a 0 value. So when the conductor is no worker, Pele, I want to teach you then sine 0 will give you 0 force because it will be parallel. Remember that. Now, just here, you guys need to understand that because you want to find force, it is pretty simple. Everything is perpendicular. So B in this is 1.5. The current in this one is 2. And the length is 4 meters. So it will be 12 newtons force that's going to act on this wire. Now, just to know that you guys know how to use the Fleming's left-hand rule, I want you guys to find out what would be the direction of force on this conductor. Quickly, please. No, Worker, we still need to do one more question. Just one more question, then I'll let you go. पहले तुम find करो जरा. Please find the force direction, and then let's see. Hurry, please. All right. It will be downwards. Let me see. Yeah, very good, kids. Excellent. It will be downwards. Very good, Zainab, Salma, Ajra, Samir. Please do it. Abu Bakr, stop being lazy. Acha, so that's good. it will be downwards. Very nice. And now let's move on to the last question that we basically want to do in this chapter. Not in this chapter, just today. Okay. So the last question that we're going to do is question number 8. Now, in this question, there is a method, and usually these sort of questions get repeated all the time. And let's see. So in this question, it says two long straight wires PQ are parallel to each other as shown. There is a current in each wire direction shown. The pattern magnetic field on the normal plane to wire due to the current is also shown. Fine, thank you. Draw an arrow to the magnetic field lines around the wire to show the direction of the field. Obviously, we're going to use the thumb rule. So what do you guys say? Where would the field be? Clockwise or anti-clockwise?
Anti-clockwise.
Yes, very good. It will be anti-clockwise. Pretty simple. Like that, just show it like this. And then it says determine the direction of force on wire Q due to this. Just want to tell you this important part. If two wires are carrying current in same direction, they attract. And if two wires are carrying current in opposite directions, they repel. Which means because they're in the same direction, so you can just draw a force like this and a force like this, and this would be it. All right, kids? Oh, direction. Oh, they said determine the direction of force on wire Q. Oh, it is to the left. So just write to the left. Like that. Then says the current in wire Q is less than the current in wire P. State and explain whether the magnitude of. Sorry, come again?
Why is it left and not right?
Because they're attracting. It's going towards the left. It says force on wire Q.
सर उसको वायर पी की फोर्स एक्सपीरियंस होगी ना तो राइट से एक्सपीरियंस कर रहा है
Who? Wire Q?
वायर क्यों
Wire P pulls wire Q. So wire P is pulling Q. This is the force from P. This is the force from Q. Bache. Do you understand?
okay
There isn't the direction in opposite.
Uh, in opposite, how? The current, both currents are going up. The same.
But the magnetic field is opposite, right?
Exactly. That's why they attract. Do you understand that? Opposite field attracts, same current attracts. Understood?
Sir, मुझे लगता है आपने ऊपर गलत लिख दिया.
Two wires are carrying current in same direction, they attract. If two wires carrying current in the opposite direction, they repel. Where?
Oh, sorry.
Is it okay now?
Yes.
Okay. All right. Nice. Oh, all right. Then it says the current in wire Q is less than the current in wire P. Fair enough. Doesn't matter. State whether the magnitude of force on wire P is less, equal, or greater. What do you guys think? Is it less, greater, equal, what?
equal
Why? Why would it be equal? They have different currents.
अच्छा
Don't you think?
ready
It will be less? Different? It will be the same. Now, let me tell you why it will be the same. Because if they're not same, it would be a direct negation of Newton's third law, right? So we're going to say, every time they ask you this question, please write that they are equal because of Newton's third law. All right. The force exerted by wire P on Q will be equal and opposite. So you're going to explain this. Opposite to force exerted by Q on P. And the reason is that this force depends on the magnetic field and the current between them. So you've got to remember this, that obviously the field and the current changes them. Force doesn't. Force has to be the same because it must obey the Newton's third law. Is it clear now?
सर ये फॉर्मूला से आपने क्या एक्सप्लेन किया है? Can you explain that
I
again?
said I said the force doesn't change. Obviously, the one that will have the greater current will have a larger field as well. Do you understand?
Yeah.
So, and vice versa. But the thing is, the force will stay the same. Is it clear?
Okay.
Never ever doubt it. Every time they ask you this, whether force is going to be equal or not, just say it's equal because you cannot go against Newton's third law. Hajra, is it clear? Everything is okay? All right. Which is very, very good, actually. Now, so the next question basically is your homework. Please try to do this. This is with the angle as well. If you could not, if you're not able to do this, please let me know. I will help you out in this one, specifically this part. So please try to do this and come back tomorrow and understand if it doesn't work. Now, then basically I want to tell you about the rest of this will be homework, but I want to specifically talk about this definition about Tesla. Now, every time you have a unit definition, all right, so they have given you unit. So basically your definition should also be in units. Now we're going to use F equals to BIL in this, and B is equal to F over IL. Now, F is basically the force which is in newtons, current in ampere, and length in meters. I wrote it down earlier as well. So please write it this way. So you're going to say 1 Tesla is equal to 1 Newton of force acting. Now, here is the key word that you guys need to remember. Perpendicular, that has a whole mark, to 1 ampere, 1 ampere current going through 1 meter of wire. So you guys need to write every unit in this, please. That's how you're going to get 3 marks, otherwise you won't. Anyhow, this question is pretty easy. You will be able to do it. Don't worry about it. It is just technical. If you still have any questions, do let me know. Okay. Finally, I want to basically go towards the last question because our worker is very, very tired and we got to move to this question. Okay. So now, in this sort of question, they said on figure 8.2, draw the pattern magnetic field produced by current carrying wires on EFGH. Fine. You know it's going up. Where do you think? What happened? Just last question, Salman. Just last question. Nothing more. So this one is like, obviously it is a clockwise, it is anti-clockwise, so it's going to be like this. Now when you're drawing these circles, just remember you have to make smaller ones first, and every time you make a new circle, just make with bigger spacing, like that. Draw the arrows, and you need to have minimum 4 lines drawn, nothing less than that, please. Finally, I just wanna just focus here. It's very important. They have given you 2 wires now. They say that the distance between them is 3.1 centimeter. One has 6.2 amperes, one has 8.5 ampere of current going through. What they then do is they give you this formula. Now, already you guys know this formula. I've taught you just today. I said do not remember this because you have this formula given. Except for the fact the value of permittivity of free space is 4 pi times 10 raised to minus 7. You guys need to remember this. Now what you do? In this question it says the magnetic flux density at a wire Q due to current in wire P. So we want to find the magnetic flux density. What it means is that obviously the wire P will have its magnetic field going through, and as the magnetic field goes through, it's gonna get interacted with the current in this wire. So we want to find this. What are they asking? They're basically asking the magnetic flux density at wire Q due to the current in wire P. So we want to find the magnetic flux density of P. So you just use basically B equals to mu naught I over 2 pi R. That is the formula right here. Now simply use 4 pi into 10 raised to power minus 7. The current in wire P is going to be 6.2. So write 6.2 divided by 2 pi, and the distance between these wires is 3.1 centimeters. So multiplied with 3.1 into 10 raised to minus 2. This whole thing should give you an answer of 4.0 into 10 raised to power 5. So this is always the first step that they're going to ask you. Write it down here. In the next one, it says force per unit length acting on the wire due to the current. Now, when they ask you force, you just use the second step, and that is F equals to BIL. Now, remember this. This magnetic field is affecting wire Q. So I want to find the force. The magnetic field at that point is 4.0 into 10 raised to minus 5. The current in Q is given as 8.5. So I'm going to use 8.5 and length because I need force per unit length. So I will just multiply these two, and that would give me something like 3.4 into 10 raised to power minus 4 Newton per meter. Then it says the currents in wire P and Q are different in magnitude. State and explain the forces per unit length on 2 wires will be different or same. Now, I do understand this. I just want to ask Abu Bakr if he says the right answer. You are all done. Yes, Abu Bakr. The ball's in your court now. No, that's, it's not fair. I've already told you, Bakar, about this. The force in both wires would be same or different. Please tell me, they have different currents. Why? So, all right, Abu Bakar, that's very bad. That's very bad. Anybody else who knows the answer to this? Why is it same, Salma? Why? Please tell Abu Bakar, because he's been dozing off in this class. Because of Newton's third law, Abu Bakar, you just know. Okay. Now, So please write this down. This is your homework as well. Now, inshallah, I will see you tomorrow and we shall continue then in finishing up this. All right. Have a nice day then.